we're going to continue looking through rotational stuff and how it relates to the linear stuff that we've already been talking about. First, in order to develop some of this, we're going to think about kinetic energy. Let's say we've got an object and it's traveling around in a circular path around some center. Now we know that the kinetic energy of this object is 1/2 mv squared. With this rotational motion, we can also think of it in rotational terms, because we can couch this in terms of angular velocity. We know that v is equal to omega r, which means this. And actually, I'm gonna use r omega when I plug it in, but so we can write this in terms of rotational motion. R omega, that becomes r squared, omega squared. And so we can also write the kinetic energy of this object as 1/2 mr squared omega squared. Obviously, this is how fast it's going, and this, and its mass, and then the radius. So there's this mr squared right here, gives us an idea of something that's important in rotational motion. This mr squared is called the moment of inertia. The variable is I for inertia. Moment of inertia. And it is, the idea of moment of inertia is equivalent to mass. Mass is how much is, in one sense, mass is a measure of how much force it takes to accelerate an object, or how hard it is to get an object started or to slow it down. Moment of inertia is a measure of how hard it is to get an object spinning or rotating, and how hard it is to slow it down. Right? The moment of inertia of multiple objects is just adding up all their mr squareds, and so for continuous objects, there's an integral that comes out as a part of figuring out the moment of inertia. So different kinds of objects have different moments of inertia. The point mass is this mr squared. In your book, on page 314, there are a bunch of moments of inertia of some regular circular sorts of objects, and for all of those, the moment of inertia is proportional to mr squared. For example, a solid disk, it's got a disk that's rotating, its moment of inertia is 1/2 mr squared. And then I believe a hollow sphere is 2/3 and a solid sphere is 2/5. They all have these different fractions out front. So then the total kinetic energy of an object can be split up into rotational and translational. So it's 1/2 I omega squared plus 1/2 mv squared. And this moment of inertia you can get from the chart on page 314, and I'll give those to you on a test or a quiz. Going back to this moment of inertia for a minute, looking at this conceptually, this tells us a couple of things. Moment of inertia is proportional to mass, of course. Makes sense that if something has more mass, it's going to be harder to rotate. The other part to this is the radius. And what this tells us is that moment of inertia goes up as mass is further from the axis of rotation. Okay. So moment of inertia contains mass, and it contains, how far the mass is from the axis of rotation. So if, for example, you have a solid object, say you have a solid cube, and then a hollow cube, oops, I screwed that up, whatever. Solid cube versus a hollow cube. The hollow cube is going to have a higher, larger fraction out in front of the moment of inertia. If they're made of the same stuff, the solid one is going to wind up having a greater moment of inertia just because it has greater mass. But if a hollow and solid thing of the same size also have the same mass, which I guess would mean the hollow one would have to be made out of something denser, the hollow one's going to have a higher moment of inertia because that mass is further from the axis of rotation. So you need to keep those sorts of things in mind for conceptual type questions. So the question I might ask you is something like asking you to determine the total kinetic energy of Earth. And, you know, Earth is both rotating on its axis and revolving around the sun. If we consult the back of our textbook, we can discover that the mass of Earth is 5.98 times 10 to the 24th kilograms. We can discover the radius of Earth, the equatorial radius, is 6.38 times 10 to the 6th. The Earth isn't a perfect sphere. And then the orbital radius, which is how far the Earth is from the sun on average, is 1.5 times 10 to the 11th meters. So we know the total KE is 1/2 mv squared plus 1/2 I omega squared. Well, Earth, if you look at the different, if you look at page 314, and you look at the different types of objects there, the Earth would be best approximated as a solid sphere, although, you know, there are the oceans and it might have a liquid core, so it's really a little more complicated than that. But the Earth would be best approximated as a solid sphere, and a solid sphere has a moment of inertia 2/5 mr squared. So it has a moment of inertia of 2/5 mr squared. And then to figure out the velocity and angular velocity, we can start thinking through some things. So the period of revolution of the Earth is 365.25 days. We usually say 365 days in a year, but it's about a quarter of a day more than that, which is why we have leap year every 4 years, incidentally. So that's our period of revolution. So if we want to get that in seconds, we're multiplying by 24 hours in a day times 3,600 seconds in an hour. Check and punch in real quick. 365.25 times 24 times 3,600 is 3,155,7,600. All right. That's how many seconds are in our year. And over the course of that year, we travel a distance of 2 pi orbital radius. So our velocity then is 2 pi 1.5 times 10 to the 11th over 3,155,7,600. Okay. Our omega is 2 pi over period, and our rotational period is about 24 hours. So we go times 3,600 seconds per hour, and so our omega is 2 pi over 24 times 3,600 radians per second. And from there we can punch in our numbers to get the total rotational, or the total kinetic energy of the Earth. 1/2, 5.98 times 10 to the 24th, times v squared, 2 pi times 1.5 times 10 to the 11th, 0.5 over 3,155,7,600 squared. Don't forget to square it. A lot of times it's easy to forget the squared when you're plugging in a bunch of stuff. Plus 1/2, and then our moment of inertia is 2/5 times m, which again is 5.98 times 10 to the 24th, times radius of the Earth squared, which is 6.38, times 10 to the 6th squared. That's another thing. This I will always contain this r squared. And since that squared isn't in the original formula, a lot of people tend to forget either to square this radius or to square the omega. So make sure you square both of them. Times 2 pi over 24 times 3600 squared. And that's an obnoxious amount of things to punch into your calculator, but it's pretty straightforward. And we can get this massively large number, 2.667 times 10 to the 33rd joules. So the Earth has a lot of kinetic energy, which one would expect because it's pretty big.